This is the last session in bending, that is chapter 4. This is the 36th session overall and the 20th session in bending. Here we will summarize the progress made and deliberate on further analysis. This is the roadmap of the first 4 chapters. We have covered 35 sessions till now, and this is the 36th session and the last session in chapter 4. In this session, we'll look back and look forward. So we'll summarize the progress and deliberate on further analysis. A similar exercise was carried out at the end of chapter 2. Here we'll briefly summarize the discussion, particularly in relation to stresses, and also refer to further examination to be carried out. A similar summary was given at the end of the second chapter. Since then, we have studied torque and bending, and our understanding has improved. Apart from internal forces, we have studied the variation of stress in circular bars subjected to torques and beams subjected to bending. So till now, we have studied stresses in bars subjected to axial loads, in circular bars subjected to torque, and beams subjected to bending. We have not looked at stresses due to shear forces. We have only partially discussed combination cases related to normal stress. General eccentric loading problems fall under these type of cases. We have not discussed combination cases related to shear stress. We have looked at deformation related to axial force and torque, but not bending. Till now, we have also not looked at pressure vessels which involve biaxial stress. Major aspects that are not being studied at this stage are energy and stability of structures. We have studied stresses for some cases and partly studied failure. Here the discussion will focus on absolute maximum stress, absolute maximum normal stress, and absolute maximum shear stress is needed to apply normal stress theory and shear stress theory. In the coming chapters, we'll look at shear stresses, transformation of stresses and failure, and other cases of combination failure. The external forces acting on a structure known, we next found the internal forces. Among the structures, finding the internal forces in a beam was more involved. These were given using bending moment and shear force diagrams. When it came to stresses, finding the stresses in a bar subjected to axial load was straightforward. So for a section perpendicular to the axis of the bar, the stress could be defined by dividing the force by the area. Finding the stresses perpendicular to the axis in a section for a bar subjected to torque or a beam subject to moment was more involved. To start with, in both these cases, we found out the variation of strain using heuristic arguments. The strain was then multiplied by the Young's modulus to give the stress as per Hooke's law. The stress variation known, we related it to the internal torque and the internal moment. Thus, we obtained the torsion formula and the flexure formula. Variation of shear stress in a beam due to shear force is found using bending moment. Shear force and bending moment are inseparably linked. We earlier came across the formula V is equal to dm by dx. The variation of shear stress at a section in a beam is found from the change in moment. For a bar subjected to an axial force, we found that the stress variation was uniform. For a circular bar subjected to torque, the stress variation at a section is given here. Only two radii are given here, but the stress variation occurs at all radii. For a beam subject to moment, this is the stress variation. Here the moment has been taken as negative, so the top portion is subjected to tensile stress. For bending, the flexure formula and as such the stress variations such as these are obtained for load applied at the axis of symmetry. In the previous slide, we discussed stresses in bars subjected to axial forces, circular bars subjected to torque, and beams subjected to moment. We need to find the absolute maximum normal stress and the absolute maximum shear stress to apply normal stress theory and shear stress theory. At the end of chapter 2, we discussed these theories of failure. After chapter 2, we have studied torque and bending. So we need to extend our discussion. Let this be a member subjected to different types of loads. Consider that at point A, we know the normal and the shear stresses acting on this element. We can rotate this element, keeping an eye on the variation of normal stress, and find the maximum, that is the principal stress. We can do the same thing for all the points in the member. That way, we can find out the absolute maximum normal stress acting on the member. As per normal stress theory, the member is considered to be safe if such a stress is less than the ultimate stress. Similarly, we can rotate this element, keeping an eye on the shear stress, and find the maximum shear stress acting at this point. The same exercise can be carried out for all the points in this member. We can then find the absolute maximum shear stress acting on this member. According to shear stress theory, such absolute maximum shear stress need to be less than an allowable shear stress for the member to be safe. Consider a bar subjected to axial loads. We take any section perpendicular to the axis such as A then all these elements are subjected to principal stresses. These principal stresses are equal and they are also the absolute maximum principal stress. Now consider a circular bar subjected to a torque. We take a section perpendicular to the axis on the portion of the bar where the torque is acting. Earlier we saw that this was the variation of stress that acts on every radii. So all points on the surface will be subjected to the absolute maximum shear stress. Consider a rectangular beam subjected to different kinds of loads acting on the vertical axis of symmetry. We can find out the bending moment variation and the shear force variation. Let the maximum bending moment be at the section AA and the maximum shear force be at the section BB. Since the maximum bending moment is at AA and considering the moment as positive, this would be the variation of stress. AA would be subjected to the maximum normal stresses in the entire beam. And these two elements will be subjected to absolute maximum normal stress, compressive and tensile, in the entire beam. We'll later see that the maximum shear stress occurs at the neutral axis. The element is shown here. Its face is aligned with the section BB, which is perpendicular to the axis of the beam. For moment, we use the normal stress theory in beam, and for shear force, we use the shear stress theory in beam. For a circular bar subject to torque, we use the shear stress theory. For these two cases where we use the normal stress theory, the sections were taken perpendicular to the axis of the beam, with the faces of the elements aligned with the sections. Also, these two cases where the shear stress theory was used, the sections were taken perpendicular to the axis of the beam, with the elements aligned with the face of the perpendicular section. So in all these cases, the points where the absolute maximum stresses occurred were found by taking perpendicular sections that is perpendicular to the axis of the beam. No rotation of the elements were required. Till now, we have individual cases, not for combination cases. Absolute maximum stress found for these individual cases are generally not at a given point. Consider the bending moment case. We earlier mentioned that the maximum bending moment was at AA. For this plane, the maximum compressive and tensile stress will be at these two elements. Now this plane can be the plane of the axis of symmetry or any plane parallel to it. So the absolute maximum normal stress will be along a whole width. Now consider combination cases. Let this be a member which is subjected to lateral loads causing bending and shear. It is also subjected to torque and axial force. It is important to remember for cases like these that the normal stresses and shear stresses do not affect each other. So if normal stresses occur at a point or different types of loads, then they can be algebraically added. If there are a number of shear stresses acting due to different types of loads at a point, then also they can be algebraically added. So consider a point in this number. Let this be the element with the stresses acting as shown. Then the normal stress is found out by algebraically summing up normal stress due to different types of loads. And the shear stress is found by algebraically summing up the shear stress due to different types of loads. That is, loads that cause shear stress. At a point when you have this stress variation on an element, then you can rotate the element and find out the maximum normal stress and the maximum shear stress. We can do this for all points in the member, and as such we can find out the absolute maximum normal stress and the absolute maximum shear stress. Till now we have dealt with cases where we have algebraically added up the normal stress due to different loads, but we have not dealt with cases where we have algebraically added up the shear stress. Consider this case of a general eccentric load acting. This loading is equivalent to a load P acting on the centroid of the section and two moments perpendicular to each other acting about the two axes. Here we have given a definite direction for the load and the moment, but in general, depending upon where this force acts and its direction, we do not know the direction of the load or of the moments. Earlier we have seen that if we take a section, this member, then the maximum tensile and compressive stresses will occur at one of the corner points for the general case. Consider this case where the moment applied is not aligned with any axis. Moment being a vector can be resolved into two moments acting about these two axes. Here a direction of moment is given, but in general we do not know the direction of the moment or that of the components. So for the general case, again, any of the four corner points will be subjected to maximum tensile and compressive stress. Earlier, we also dealt with the unsymmetrical section. With an unsymmetrical section, we first need to find out the principal centroidal axis with the product of inertia zero. If the moment applied does not align with any of the two axes, then as before, it can be resolved to moments that act along the two axes. We can use the flexure formula and add the stresses algebraically. As we have seen with examples, for these cases, we do not know the point where the maximum or absolute maximum stresses will act. Consider this case. If we take a section, say somewhere here, then the same corner point will be subjected to maximum tensile and compressive stress, and the magnitude will be same. In contrast, in this case, there's only one section which has the absolute maximum stress, though the points are all along the width. We also can have a case like this, where there are transverse loads acting on both the axes of symmetry. Then we have to develop bending moment diagrams for this axis of symmetry and also for this axis of symmetry. In this case, the absolute maximum normal stress will be at only one point. We discuss the neutral axis for different cases here. The neutral axis has importance in bending, particularly with unsymmetric bending, as we have seen. It varies based on the loading and the geometry of the section. Also, it varies depending upon whether the beam is straight or curved. We start with a straightforward case where a moment is applied about an axis of symmetry. If we consider a section here, then this is the variation of stress. The axis of symmetry is the centroidal axis here, and it coincides with the neutral axis. Here we have another case where there's a moment applied about an axis of symmetry, but we also have axial load acting. Again, we consider a section as shown. Then at this section, this is the stress due to bending, and this is the stress due to axial force. As such, this is the stress acting on the section. Since the axial force acting is compressive, with compressive stress, the neutral axis has moved downwards. If this axial force were tensile, then the neutral axis would have moved upwards. Neutral axis does not coincide but stays parallel. Here we have two moments acting about the two axes of symmetry. Consider the stresses acting on this section. Then the neutral axis shown here is the axis of zero stress. It passes through the centroid. However, it is at an angle to the axis of symmetry. We have dealt with problems where we find this angle compared to the horizontal. Here we have moments about both the axis of symmetry and axial load acting. If we consider a section here, then the stresses acting will have a line of zero stress on neutral axis as shown. It is both inclined to the axis of symmetry and does not pass through the centroid. Hence, it has attributes of both these cases. Then axial force acting along with moments, the neutral axis does not pass through the centroid, as shown here. And with moments acting about both axes of symmetry, the neutral axis is at an angle to the axis of symmetry or centroidal axis. With an unsymmetric section, as we saw earlier, we have to find out the position of the principal centroidal axis. If the moment vector acts along any of these principal centroidal axes, would be the axis of zero stress or neutral axis. Over here we have shown moment acting about both the principal centroidal axis. If we consider a section here, then the line of zero stress will not coincide with any of the principal centroidal axis. Till now, we have been discussing about the neutral axis of a section. However, with the curved beam, we'll discuss about the neutral axis of the beam and also the centroidal axis of the beam. As we can see, for a curved beam, the neutral axis does not coincide with the centroidal axis. So if we consider the neutral axis after a moment has been applied, it has a different radius of curvature. So this radius of curvature. The curved beam loading is considered to be applied at the axis of symmetry.